Hello everyone. So today we are going to look at a problem, a number of ways to arrive at destination. This is a Leetcode problem 1976 code. So this is the problem statement and we are given an example over here. So let's see. So the problem statement says that you are in a city that consists of n intersections numbered from 0 to n minus 1. So these are the n intersections, okay, 0 till n minus 1, which is 7 minus 1, which is 6 in this case. So the inputs are generated so that you can reach any intersection from any other intersection. There is at most one road between any two intersections. So between 0 to 1, there will be at most one road or there will be no node. For example, between 0 to 2, there is no node, right? So you are given an integer n and a 2D integer array roads, okay, where roads I equal to ui comma vi comma time I. Okay, so for example, in this case, roads equal to 0 comma 6 comma 7, which means that from 0 to 6 there is a edge which is of weight 7. Okay, 0 to 6 weight 7. This 7 is a time. Okay, how much time it takes from 0 to 6. Similarly, from 0 to 4 it takes 5. Okay, so you want to know in how many ways you can travel from intersection 0 to intersection n minus 1 in the shortest amount of time. Okay, so there can be multiple ways, right? We can reach from 0 to 6 for the same time, for the 7, right? If you see in this example, if we go directly from 0 to 6, how much time it takes? It takes 7. From 0 to 4, 4 to 6, how much time it takes? 5 plus 2, 7. From 0 to 1, 1 to 3, 3 to 5, 5 to 6, it also takes 7 minutes. From 0 to 1, 1 to 2, 2 to 5, 5 to 6, it also takes 7 minutes. So as you can see, there are multiple paths to it. So there are 4 ways in this case from 0 to 6. So our answer will be 4. Okay, so if you will notice carefully, right? So in Dijkstra's algorithm, what we used to do was we just need to find the shortest path, that is 7. Okay, and once that 7 is found, we just return it. Okay, the shortest time or the shortest distance is 7. Here it is an extension of Dijkstra's algorithm where we just don't have to find this 7 minimum number. We have to find the number of ways this like how many 7 can occur, how many shortest time can occur. Okay, so we have to find all those paths, the count of all those paths. So it's just a minor modification of Dijkstra's algorithm. We will see later on. Okay, so first let's see how our regular Dijkstra's algorithm will work and which will help us in figuring out the 7 number. Okay, so yeah. So what happened is I have removed all the edges. 0 is my source, 6 is my destination. So I'm taking two arrays. Okay, so in the first array I am checking whether that node is explored or not. Okay, I will start from the 0th node. I will see whether that node is explored or not, and the second array tells me that what is the shortest time to reach from 0 to that node. Okay, in this case, if you will see, from 0 to 0, shortest time will be 0, right? And from rest all these I have make it infinity, that there is, since there is no edge, right, we cannot reach to that node. So that's why from 0 to all other nodes it will be infinity. And I have initialized all of these to false, that we haven't explored any node. Okay, so now what happened is I explored the 0th node, the first node. I will pick the first node, I will explore it, the source node. So after exploring it, I will mark it to true. Okay, and from 0 to 4, okay, how much time it took? If you will see, from 0 to 4 it takes 5. Okay, from 0 to 4 it takes 5. I have updated on 4 this 5. From 0 to 6 it is 7. From 0 to 6 it is 7. So I have updated the 6th node as 7, that it takes 7 seconds to reach till 6. Okay, and from 0 to 1 how much time it takes? 0 to 1 it takes 2 seconds. So I have updated it to 2. Okay, till it's clear, right? Till now it's clear. So over here I have marked it as explored. Now the trick comes over here is that from this node, right, I will pick the minimum, the shortest time which took. So shortest one is the first node. Okay, so it took just 2 seconds. From 0 to 1 it took 2 seconds. That means that there cannot be other path till 1 such that it takes less than 2 seconds. So this is the minimum time it will take, definitely not less than that. Okay, 2 seconds is the minimum time to reach from 0 to 1. So that's why we will pick the minimum node. So the minimum node we picked over here is the 1. Okay, now we will explore 1. After exploring 1, we will mark it as true, that this node is explored. Okay, so that we are maintaining it so that we don't reprocess it again. Okay, that's why we have to maintain it. So we explore this one node, and from 1 to 3, right, we will see that, okay, 1 to 3, this the distance is 3. Okay, till 1, what's the distance? Till 1, the distance is true, and 1 to 3 is 1 to 3 is 3. So 3 plus 2, 5. So we updated it to 5. And 1 to 2. Okay. 1 to 2 is 3. So 2 plus 3, 5. So we have updated to 2 also, 5. Okay. So now this is our updated array. Now we will pick the minimum from here, right? So why we are picking minimum? Because that node cannot go any further minimum to that. Okay, that's why we are picking that, because no other, from if we try to reach from any other node, it will always be maximum, like it will always plus it, because there are no negative edges, right? So we will keep on doing it. You see over here, now we pick the 2 because it has the minimum. We could have picked any of this out of 2, 3, 4. We picked the 2, and then we marked it true, and then we explored from 2 to 5. Okay, from 2 to 5, how much time it takes? 1. Okay, from 2 to 5 it takes 1. Till 2, how much time it takes? Till 2 it takes 5. Okay, so till 2 it takes 5. So 5 plus 1 is 6. So we updated the fifth node as 6. Okay, so let us suppose there was some, like, if we add it, if there is some larger value than 6, 8. Okay, and there was 6 already present over here, then we will not update it, because we always want to find the shortest time to reach that node. Okay, so we will always take value whatever is present over here, and whatever we calculated, that from 2 to 5, whatever we calculated, shall we update it or not? Okay, so over here, what is the minimum? The minimum is, we have to also check whether that node is explored or not. We have to pick only the unexplored node. So out of 3 or 4 only we can pick. So out of 3 and 4, we can pick the third one. Okay, similarly we can mark it true and explore the the below edges, below nodes. Okay, explore the below nodes and update its value. Okay, so we updated the 6 and 5 value over here. Okay, so we updated the 6 to 7. Okay, the 6 is updated to 7 because till 3, how much is the path? 5. Okay, and from what do we say, from 3 to 6 it is 8, right? Since the 6 already has 7, right, if you will see in the previous diagram, so since 6 already has 7, so we will not update it. Okay, so we updated it earlier only. Okay, when we directly reached from 0 to 6. Okay, so there is no need to update this 6. So similarly we will keep on doing it. Okay, now we explored this 4, and now we explored this 5. Okay, so that's it. So now we will come to know that what's the minimum shortest time to reach this node. We will just see this value. Okay, shortest time is 7. So this is how the regular Dijkstra's algorithm work. And in order to find the minimum, right, we have to traverse the whole array, so that will take a lot of time, that is take order of n. So instead of that, we can use the priority queue, in which the minimum it's log of n. So we take an additional priority queue for that. That's the regular Dijkstra's algorithm. Now here what we have to do is we have to find the number of ways on reaching 6. So if we know the number of ways of reaching 3, number of ways of reaching 5, and number of ways of reaching 4, right? So we can easily come to know what are the number of ways of reaching 6, right? And we have to find that whatever is the minimum time to reach to the 6, right? We have to increment that count only. Let us suppose there is a path from 0 to 1 to 3 to 6, right? This takes 8. So we don't have to consider this 3 while calculating the number of paths, because it is 8, right? And we already have a path which is coming out as 7. So we have to increment only that path for which this is minimum. Okay, like from 0 to 4 to 6, okay, this is one path. Okay, then this was minimum, it was 7, right? 5 plus 2, 7. Similarly, if you will see over here, 0 to 1 to 3 to 5 to 6, we reach here, we will increment it because it is minimum, then only increment it. 0 to 1 to 2 to 5 to 6, increment it. If you find that you have found even smaller value, then reset the count. Okay, reset the count to, we will start again. Okay, you see 0 to 1 to 3 to 6, it is 8. So we will not increment it. Okay, we will just discard this. Okay, so if we have to show, So we have maintained one additional vector or array, okay, where we are saying that what is the shortest time for that node. In this, what is the shortest time for this 0? The count of short number of ways of reaching this 0 with that shortest time is in this case is 1, because there is only one way of reaching, right, which is itself. Now from 0 to 4, 0 to 6, 0 to 1, there is only one way of reaching this, right, with the minimum time. So we updated it to 1, 1, 1, 1, okay. So now rest all remains the same. Now from 1 to 3 and 1 to 2, there is again only one path, okay. So we updated it 1, 1, 1, 1, 1, okay, to 3 and 2 basically. 3 and 2, we updated it to 1. Now let's see further. Now to 5, okay, 5 also we updated it to 1, okay. There is only one way of shortest time, okay. Now again let's see. So over here, if you will see, now we can reach from 0 to 1 to 3 to 5 through this also, right? So here that's why we incremented this 5, okay. When we were like exploring this edge, we again encountered this 5. We checked what's the value of 5. The value of 5 was 6, okay, because it was, we explored earlier from here, right? 2 plus 3 plus 4. Now when we started exploring here, it was also coming out to be 6, okay. That means there are two ways of reaching over here, okay. 6, that's why we incremented the count. With the same time 6, there are two ways of reaching over here, so we incremented it to 2. Now again, if you will see in the next question, in the next diagram, so 4 to 6, we explored that and we updated it to 2, okay, because earlier 0 to 6 we had a path where it was giving 7. Now we have 0 to 4, 4 to 6 is also giving 7, right? So that's why we incremented it, because the value is same, okay, 7. So we incremented it. Now the last part from 5 to 6, okay, from 5 to 6, what we will do? 6 already has 2, okay, you will see 6 already has 2. Now 5 to 6, what is the minimum time to reach 5? It is 6. And how many ways are there? 2 ways. Now from 5 to 6, how many ways will be there? 2 ways. So from 5 to 6 there are 2 ways, and from till 6 there were already 2 ways which was present, 0 to 6 and 0 to 4 to 6. So 2 plus 2, we will do it 4, okay. So our answer will be the n minus 1, the last destination node we have to find, right? Whatever is the value over here will be the answer, which is 4 in this case. So if we have to see the solution, right? So solution will be like, first of all, we will create the graph. Okay, we are given a vector of roads, right? The first node, second, this is the first node. We are approaching the second node. Third is the weight. Similarly, since this is an undirected edge, we reverse it. Second node, first node, and the weight. Okay. Then what we have maintaining is whether that node is explored, what is the shortest time to reach that node, and the number of ways to reach the node with the shortest time. Okay, these are the three arrays, and this is the priority queue. Why we have maintained a priority queue? In order to find the shortest time. Okay, so that we can find the shortest time in log n. So we have initialized for this 0, for the 0th node, which is shortest time to reach node of 0 is 0. Number of ways to reach node with the shortest time 0 is 1 itself. That is the single way, and we will push in the priority queue this 0, 0. And now here comes the logic. What is the logic? That we will keep on iterating it till this priority queue doesn't become empty. Okay, we will check if the node is already explored. Okay, we will skip that. Otherwise, we will check all its adjacent edges. Okay, all its adjacent edges, and for each of those edges, we will see that if that node is already explored, then we will say continue. Okay, if that node is not explored, then what we will do is we will calculate the total time to reach that node. If that total time is already equal to the shortest time, okay, if the total time is already equal to the shortest time, then we will increment the number of ways. Okay, how we will increment the number of ways? Whatever number of ways was present on that node plus the new number of ways which are coming from the previous node. So we are adding these two. Okay, if you will see the diagram over here, so whatever was present on the 6 and whatever came from 5, we added both of these, right? That's what we are doing over here. This is that case. Otherwise, if the total time is less, that is, we have found a path which is even lesser, okay, that means we have to reset it. Reset it means we just have to put the value to this number of with the previous, like whatever, let us suppose this in this 6, right, 0 was present. So what we would have done is whatever was the value over here at 5, we would have put it over here at 6, because there is no other path. So whatever are the paths from 5 will be the paths of the 6. Okay, because it will come from 5 only, right, the shortest one. So that's why this is the else case. Rest, then we will mark this node as explored true and the shortest time node dot pop. And percentage mod we are doing because there is a condition that because it can breach the int, right? So we are doing the percentage mod, if you will see the question. So this is the first approach. Here you will see that we are maintaining an extra explode node, right? So this could have been further optimized. If you will see over here, right? Here we are, this is the full complete code. Sorry, this is the complete code which of this, you can see this, okay? And this is the second implementation. You see that here we are not taking this, is node explode, okay? So how will we check whether that node is explode or not, okay, so that we don't reprocess it? So this is the condition for that, okay? So whenever we will add the node, same node again, right, so its time will always increase, okay? Whenever we reprocess the same node, its new time will always increase. So when its new time will always increase, then we will come to know that it's an outdated node. So this is the main condition over here. Rest of the logic is absolutely same, okay? Now coming on to the time complexity. So the time complexity for building this graph will be order of v, which is the number of edges, okay? And according to Dijkstra algorithm, okay, so it's order of v plus e times log v. Total complexity will be the max of these, okay? Though not the max, basically we will do the plus, and it comes out to be order of v plus e log v, okay? Now, how this comes, order of v plus e log v, it is broken down into two parts, v log v plus e log v. So how v log v comes? V log v comes because whenever the node is pushed into min heap, right, every node is pushed at most once. So how many nodes are there? Okay, there are v nodes, okay? And how much time it takes to extract the minimum element from the heap? It takes order of log v, okay? So total time complexity will be v log v, because there can be max v nodes. Time to extract will be log v o log v. Similarly for the edge, right, so every edge is processed at most once, okay? So every edge is processed at most once. So and we explore every node's neighbor, okay? There is a for loop, right, inside our if you see our code over here, there is a for loop over here where we are processing every edge. So that's why this is saying order of e times log v, okay? Because push and update operation takes log v times. So the total complexity, we will add it, v log v plus e log v, which is v plus e log v. Now coming on to space complexity. Space complexity is pretty simple because graph representation is order of v plus e, and for the priority queue and other data structures, since we are taking just whatever the number of nodes count are there, we are taking that complexity. So the total complexity will be order of v plus e. Thank you so much.